For 7 years, something in the sky has been reaching down and scrambling GPS across an entire continent in bursts that last only a few seconds. Nobody knew what it was. Now, a team of researchers thinks they've caught it, and their prime suspect is a Russian satellite built to watch for incoming nuclear missiles. The work comes from a new paper called Chasing Lightning out of the University of Texas at Austin and Stanford. And the title is a clue. Lightning is a nod to Molniya orbits, because Molniya means lightning in Russian. Hold on to that, because it matters later. Here's what they found. Since 2019, GPS receivers scattered across Europe, Greenland, and Canada have been getting hit by sudden, powerful bursts of interference. Each one drops the signal quality hard, then vanishes within a few seconds. The team combed through data from 165 high-rate reference stations going back to January 2019 and pinned down 75 separate days with one of these wide-area events. And the strange part is how synchronized they were. In one 2021 case, stations in Finland, Italy, and Greenland all saw the same degradation at essentially the same instant, lasting about 3 seconds. One event that day was picked up by 58 stations at once. Now, before we get into why that points to space, let's talk about how GPS jamming normally works, because that's the rule this breaks. A typical GPS jammer is local. Think of the little illegal units truckers buy, or a military jammer on a battlefield. They drown out the faint satellite signal with noise, but their reach is tightly limited by power, antenna height, terrain, and the curvature of the Earth. A ground jammer can mess up a city, a highway, a harbor, maybe aircraft in line of sight. What it physically cannot do is hit Finland, Italy, and Greenland in the same 3-second window. The Earth bulges between them. No single ground unit, ship, or aircraft can see all of those places at once. So that's the break. The footprint is simply too big for anything on the ground. To cover that whole region, from the Mediterranean to the Arctic, you'd need a chain of perfectly coordinated jammers stretched across thousands of miles, all firing in the same second, and then all going quiet together. Or you need one thing parked high above it all, looking down on a huge slice of the planet at once. Now let's talk about what's actually getting hit, because the precision here is the second big clue. The interference lands right around GPS L1. That's the workhorse civilian GPS frequency, centered at 1575 megahertz, and it's the band underneath aviation, shipping, financial timing, and basically the invisible scaffolding of modern infrastructure. The paper found the interference peak sitting just above it, around 1577.5 megahertz, about 5 megahertz wide, close enough to also degrade Europe's Galileo and China's Beidou signals nearby. This isn't vague GPS got weird data. It's a repeatable, structured fingerprint in a very specific place on the dial. The natural first suspect for anything this wide and sudden is the sun. Solar radio bursts really can knock out GPS across the daylit side of the planet. So the team checked and the signal doesn't fit. A solar burst is broadband, it smears across all the GNSS frequencies, it builds and fades slowly, and it lasts for hundreds of seconds. They compared the mystery signal against a real solar flare from November 2025, and the two look nothing alike. The mystery signal is short, sharp, narrow, and it keeps returning to the same frequency. Solar storms can scramble GPS, but this isn't one. There were other fingerprints too. The bursts clustered hardest over the Baltic region, with the single biggest drop recorded at a station in Poland. And within a given day, the big bursts often arrived on a clock, spaced by exact multiples of 150 seconds. Random space weather doesn't keep a schedule like that. That rhythm hints at a machine running a pattern. So, how do you track a 3-second burst back to a specific object in orbit? The team used 3 layers of detective work. First, geometry. For a satellite to be the culprit, it has to be above the horizon for every station that got hit, which trims the suspect list fast. Second, power patterns. The strength of the interference at each station depends on where the satellite is and how far the signal traveled, so they modeled which orbiting object best explained the spread. And third, the clincher, time difference of arrival. If two separate receivers record the same burst, the signal reaches the closer one a hair earlier than the farther one. That tiny time gap is a fingerprint of the source's location. Line it up against the known positions of satellites overhead, and you can ask which one fits. That brings us to February 11, 2026. The smoking gun. On that day, two wideband receivers, one in Amsterdam and one in Trondheim, Norway, both captured raw samples of the same interference event. The team ran their time difference analysis against every candidate satellite overhead, and only one passed their statistical bar. A satellite called Cosmos 2546. The match was so strong that, in their words, the probability came out essentially indistinguishable from certainty. You could inflate the assumed error in the satellite's position from 10 kilometers all the way to 500 kilometers before any other object even became a plausible alternative. So what is Cosmos 2546? It's part of Russia's EKS network, an early warning constellation designed to spot the heat plume of a launching missile. These satellites ride Molniya orbits, those highly elliptical paths that let them hang for hours high over the far north, and that is exactly the geometry you'd want to blanket Europe, Greenland, and Canada with a signal at the same time. But here's where the team is careful, and we should be too. Cosmos 2546 didn't launch until May 2020, and the interference goes back to 2019, so it can't be the single source of everything. Instead, they argue the whole EKS constellation is collectively responsible. Across all 75 event days, at least one EKS satellite was sitting high in the sky, above 35 degrees, for every affected station. The fingerprint follows the constellation. Now, the part that's easy to oversell, this paper does not prove Russia is deliberately attacking GPS from space. It identifies the source. It does not establish intent. We don't know if this is a weapon, a test mode, a side effect of the radar payload, signal leakage, or a malfunction. The authors are clear that if it's deliberate, it would be a serious escalation. So what do you think is going on up there? A deliberate signal, a leaky payload, or something nobody's figured out yet? Drop your theory in the comments and let me know which camp you're in. And if you want more breakdowns like this, smash that like button